Hi all, I'm Pietro Ferrara and today we'll present you my SAC paper in the SVT track that is about cross-program taint analysis for IoT systems. This is a joint work with Amit Mandal, Yuli Klebnikov, Agostino Cortesi and Fausto Spoto. So first of all, let's start from the end of the title, IoT systems. So how is composed an IoT system, first of all? Essentially, what we have in existing IoT software and systems that we see around is a bunch of different layers. So we have devices, usually with embedded sensor and actuators, so with embedded software managing the device and interacting with the physical world exactly through sensors that read the status of the physical world and actuators that change the physical world outside there. Usually the devices are locally connected through a gateway, like, I don't know, Wi-Fi router or these kind of things. And the gateway also is the gate in order to be connected to internet, to cloud platforms around. On the right side, what we have is a lot of applications that remotely want to supervise, manage the IoT physical system that we have on the left side. So you have applications like web applications rather than mobile application and these kind of things. How this translates into software? Essentially, this translates into several different layers. So usually, first of all, on the physical device, we have some embedded software. Then in the back end of the IoT system, usually we have something, some edge software, so-called edge software running locally on the local gateway. Then, of course, this communicates with the cloud. So often we have cloud storage services that might be accessed like for web applications rather than for other web services that might be used for other purposes like mobile applications. This is just one possible architecture. The main point is that when we moved into software for IoT systems, at different nodes of this schema, what you get is different software. Okay. Then let's move to the first part of the title. So let's talk about the taint analysis. Here I'm making a very short introduction. If you are not familiar with these topics, I think you can find a lot of materials around. But in general, taint analysis is targeting to detect if something that is tainted, starting from a source, could flow into a sink without being sanitized. This is a very generic definition of the taint analysis problem, and we are talking about static taint analysis. So we want to prove this property statically, that is, without executing the program. Over the last 2 decades, taint analysis has been widely applied for security vulnerabilities, mostly in web applications. So first of all, for various types of injections. How do we instantiate this very generic statement to these types of properties? Well, let's think about SQL injection. When we are dealing with SQL injection, taint analysis is phrased with something like, we want to detect if something that is coming from user input, so from APIs reading user input, like, I don't know, read line, rather than reading parameters of a Java servlet, could flow into a method executing a database query, like, execute query, for instance, without being properly escaped. So using common APIs or by manually checking the content of the string and adding the proper escaping with respect to the SQL language. We can also instantiate, and it has been widely instantiated, this type of statement for cross-site scripting. Here, the sources are still user input, but the sinks are not anymore methods executing a database query, rather than methods executing, for instance, some JavaScript code, like, document write or whatever. So putting something inside a web page that could be executed client-side in a browser, without being properly escaped with respect to the cross-site scripting context we are looking for. So, for instance, escaped for JavaScript programs. Starting from this, we have also quite a lot of IoT vulnerabilities. So maybe you have already heard a lot about the OWASP top 10 list of vulnerabilities. This has been around for like a decade, and it's the list of the 10 most, let's say, warning, most dangerous security vulnerabilities you might have in web applications. Several years ago, the OWASP Foundation started also a project, an IoT project, that led already in 2014, and then the list was revised a couple of years ago, to a list of the 10 most dangerous vulnerabilities in IoT software. Okay, here we have a complete list. Some of them are more about, passwords, like if you are familiar with security vulnerabilities of IoT software, you have for sure heard about the Mirai attack that was based on guessable or hard-coded passwords, weak especially passwords, rather than other types of problems that are also quite popular, unfortunately, for web applications, like using insecure or outdated components. However, for the purposes of this talk and the purposes for which we want to apply taint analysis to IoT programs, we stay on the third vulnerability that is listed by the IoT top 10 listing. That is the insecure ecosystem interface. How is this defined? Essentially, this says that some levels of interfaces inside the IoT ecosystem might be vulnerable with respect to many different types of vulnerabilities, in particular because of the lack of input and output filtering. Okay, so it's enough to have that one of the layers of the IoT software I introduced to you a couple of slides ago is vulnerable, and this might compromise the whole reliability and security of the IoT system. What is around with existing taint analysis by now? The idea is that when we run a taint analysis, we just track one bit per variable, a Boolean flag, because we want just to track for each variable if it might contain tainted data, so data coming from a source, propagate it through all the program, and then check if it might flow into a sink. Of course, the existing taint analysis engines we have, they reason about a single program. So let's take this snippet of code. Okay, this is taken from some edge software in IoT system. In this case, we have a socket that is reading some input stream, and this is the source of our taint analysis. Then what our taint analysis engine does is to propagate it. So this is assigned to variable IS1, that is then passed to a constructor and it flows into ISR1, then BR1, then we go into message 1, then we split message 1, so this tainted data flows into R1, then this is parsed, so also the local variable hum that represents the humidity is tainted, then it is passed to a method, it flows into a put, the representation of a put in a table, and then this is added to the table. And then this is also what we consider as a sink, so an existing taint analysis engine would be able to conclude that we get something from a source flowing into a sink. Julia implements a taint analysis engine. Here I put you some bibliography, so if you are curious about all the aspects of the Julia static analyzer, you can read these papers. What is important is that, first of all, it's a commercial static analyzer, so Julia scales up to real-world applications made by hundreds of thousands lines of code for object-oriented programs, so Java, also Android, and .NET programs. It contains inside a formal rigorous taint analysis engine. Starting from the results of this engine, it can reconstruct the flow of tainted data. So like in the previous slide, it's able to reconstruct this complete flow of the tainted data inside the program. And it also allows to define different types of sources and sinks. Like, for instance, let's say in a context of detection of leakages of sensitive data, we might instantiate the analysis saying, look, I don't know, the method getName returns the name, getSurname returns the surname, and then we have different leakage points. So we might have the database when you execute a query rather than internet when you pass something to a URL or to the response of a servlet. So, As we have seen, the existing taint analysis, what does is we can define something of a given source type. So let's say that we know that through this socket we have a source of type sensor. We can also specify in Julia's taint analysis that we have different sink types. So in particular, the parameter passed to the put is a sink of type database. And then, thanks to the taint analysis engine I just discussed with you, we can have this complete flow of information and see that we have something that from a sensor flows into a database. So we can have warnings reporting exactly this type of flows and also the complete flow of information. As I already said, in an IoT application we have several different layers of software. The data flows through these different layers through different communication channels. So for instance, here we have an IoT backend that directly interacts with different physical components that interface with the real world, with the physical world, with sensors and actuators. Then this backend stores the data into a database through the cloud storage, and then a servlet accesses these databases and exposes some information through like standard internet channels, like, I don't know, through a servlet, request and response parameters. And then maybe we have a JSP page and Android application that are both accessible by users that might use this to both see the values of the sensors of our IoT system and also take action, like, I don't know, switch on or off a light in the IoT physical system through different actuators. What is also important is that only very few layers inside an IoT application communicate with the external world, and the external world, let's say, is a physical world or the users of the IoT system. What are the main limits of existing taint analysis engine when we apply them to IoT system? The problem is that taint analysis covers if something from a source flows into a sink. IoT systems have at least two different types of sources and sinks. One is involving external components interacting in some ways with the real world or with users. So for instance, the real world might be a physical system. So like we might have the APIs reading sensors as a source and the APIs passing values to actuators as a sink of our taint analysis engine. Or we might have, for instance, JSP pages or Android applications where we might have also different type of sources. Let's say a get location in Android is usually a source of sensitive data. And we might have also different things like, you set a label, so these things will be visualized to the user, so it will be exposed to the external world, so it's a sink. The second type, let's say macro type of sources and sinks involves communication channels. So for instance, we might have communications between different layers of the IoT application that communicate through the database. So like if you do a result set.get, this is a source from the database, or execute update would be a sink to the database. Or internet, you do request.get, it's a source of information retrieved through the communication channel internet. Or response.put is a sink because the information is then communicated through internet. The goal of our work is to extend existing taint analysis to discover IoT vulnerabilities. This is the algorithm as it's described in the paper. Let me explain very briefly, intuitively, what it does. First of all, let's start from the input. We have three inputs. One is the set of the applications of different layers of our IoT system. Then we need to know the external sources and sinks, like reading the values of sensors or leaking information through a set label in an Android application. And then we need a definition of all the communication channels together with the sources and sinks. So here we might have a database where the source is the result set.get and the sink would be the execute update on the database. Then what this algorithm does is, first of all, we consider both the external and the communication channels, sources and sinks in our analysis. We configure the analysis using this information. So we rely on Julia's configuration that allows us to say, look, some of these sources and sinks are of type, for instance, sensors or Android UI elements, so they have to be considered external. Some others, like database, internet, instead are just internal communication channels, so they are from a different type. And then we run the analysis here at line 6 with Julia. We then discover the connection through communication channels between different layers of the applications. We check as a whole graph, then finally, if an external sink is reachable from an external source, passing over several layers of our software, in particular through some of these communication channels. This is rather theoretical concept. How it works in practice? We have a running example. I'm not going to introduce you the code that we have in the paper. Just read the paper and we see the minor details. But what we do is, first of all, we start by defining the sources and sinks. And for this particular example, what we have is, we have a socket get input stream that is an external source of type sensor. We have table.put that is a database sink as a communication channel. We have the execute query that retrieves data, so it's a source of type database communication channel. We have the writer to a servlet.write that is a sink through the internet communication channels. We have a worker that retrieves data through internet, so it's a source of internet communication channel of information. And then we have the set text in a text view in Android that is an external sink of type Android text view. So more or less, these three programs represent exactly the edge software, the Java servlet, and the Android applications of the examples I discussed at the very beginning of this talk. Then what we do is we just run the taint analysis engine of Julia and we discover these flows of information internally at each program. So here we are running state-of-the-art taint analysis engine in order to discover inside a single program if there are flows from sources to sinks, where sources might be and sinks might be both external or for internal communication channels. Then essentially our algorithm, what it does, we more or less abstract away the whole program and we just connect the different communication channels. So here we can see that we have some information from a sensor that flows inside the edge software to the database. Then we have the Java servlet that reads from the database and let this information flows to internet. And then we have an Android application that receives this information from internet and it leaks it through an Android text view component that is an external sink. So this is the CrossProgram algorithm. And what we end up is that we discover a flow of external source information, so from a source to an external sink to an Android text view, and therefore we can say we found kind of a vulnerability. This is just to give you the intuition. What we've done was to apply to this approach to several different applications, 5, that we think were quite representative because they deal with the different types of communication channels. So 2 of them are with Firebase, one is NFC, one Bluetooth, and one Internet. Okay, they were made always by at least 2 applications. They are all published in GitHub, so you can access them and see what types of software is. And in 4 out of 5 cases, we found potentially dangerous flows. Like, for instance, we have the doorbell. What is the doorbell application? Essentially, when somebody rings your bell at your home, in your mobile phone, you can see the video camera of your surveillance video camera, and then you can decide if you want to open or not the door. So our analysis exactly discovered that there was a flow that was going from the picture, the surveillance camera of the IoT system to the mobile application. And similar flows were discovered in the other cases. So there were 4 potentially dangerous flows, but they were all needed in order to implement the main functionality of the IoT system that was under analysis. For Robocar, we didn't discover any flow, and also this was intended. When we analyzed in details the program, we realized that was correct. because essentially the robocar was not letting flow in directly information, user input to actuators of the IoT system, but it was properly making a lot of checks over these values and sanitizing these elements in order not to have any dangerous flows. We have submitted, and the paper has been accepted for publication in one of the next volumes of STTT. So the full details about the 5 experiments will be published there, as well as many other discussions, especially about the IoT top 10 listing made by OWASP. Last but not least, some future work. So for now, our approach considers a full communication channel as tainted. Something flows to a database, then the database is tainted. Somebody is reading information from the database, then everything from that database is tainted. This is fine for the examples we analyzed and the systems that we were considering, but usually only a part contains sensitive data or user input. So for instance, when I put something in a database, I'm putting it in a specific table, in a specific column of that database. Rather than I pass some sensitive data through a specific parameter of a servlet response, and then when it's accessed, only if I access the specific parameter of the server request, I would have tainted the data. In order to deal with this statically, we need a really specific ad hoc string analysis to precisely track these cases. And why I'm saying string analysis? Because usually what we observed is that all the communication through this channel happens through values that are coded in the forms of string. So it's really important to have a precise analysis over string values. And this is exactly what we are doing right now at University of Venice. We have a bunch of ideas and we are starting also to implement them and make experiment out of that. Well, this ends my talk. I hope you enjoyed it. If you want to have more details about the work, just, of course, read the paper or just ping me. My email address is pietro.ferrara@unive.it. And hope you enjoyed the talk. Bye.